Glass fibers are added to plastic materials because they stiffen parts and help them stand up to external loads without excessive deflection. To get that benefit, the fibers must be oriented in the correct direction. When designing a part, how do you know that you'll get increased part strength and stiffness where you need it? With Moldex3D, we can consider the fiber orientation effect. The fiber analysis add-on is needed for this type of analysis. Simulations with this parameter enabled will show the part's anisotropic and non-homogeneous properties. Anisotropic is a term referring to materials that have different physical properties depending on which direction they're measured in. An example is wood, which is stronger along the grain than across it. Non-homogeneous means that the properties are non-uniform throughout the part. Using wood as an example again, the hardness is non-uniform. The darker growth rings are harder compared to the lighter growth rings. For this discussion, modulus is the anisotropic and non-homogeneous property that we'll be focusing on. Let's start by defining modulus. Modulus is a measure of stiffness. A stiffer material is associated with a high modulus, and a softer material is associated with a low modulus. The modulus in the direction of fiber orientation will be higher because the fibers are stiffer than the plastic that they reinforce. Moldex3D shows several different modulus results. We can show each component in the X, Y, or Z direction of the modulus distribution, as well as the major, minor, and mean modulus. The major modulus result shows the distribution of the modulus in the major direction of fiber orientation. Due to the highest degree of fiber orientation, the stiffness in this direction is also the highest. The minor modulus result shows the distribution of the modulus in the direction with the lowest fiber orientation, which is the least stiff. And the mean modulus result shows the distribution of the modulus in the direction with the second highest fiber orientation. The modulus will be affected by molding condition as well as gate location. On the left, we've got our default process with one gate. In the center, a fast fill with one gate, and on the right, two gates with the default process. Looking at the major modulus, we see that the part on the left has the highest modulus in the center of the bar. This means that when an external load is applied to the bars, the one on the left should deflect the least. But let's take a closer look using the clipping tool. You can just rotate with your mouse, or like what I'm doing here, use the view control window to select the angle you'd like. You can save this view for later if you'd like to return to it again. Zooming into the weld line area, I'd like to compare the X, Y, and Z modulus for these three parts. In the X direction, the modulus of the weld line is a bit higher than the two parts without the weld line. In the Y direction, the modulus is significantly higher than the two without the weld line. And in the Z direction, the modulus is significantly lower than the two without the weld line. So looking back at the major modulus results, we know that it's showing the modulus in the direction of highest fiber orientation. For the two parts on the left with no weld line, that's going to be the Z direction. But for the part with the weld line on the right, that's actually going to be the Y direction. So it's important to make sure you understand which direction is the direction of major fiber orientation before using the major modulus results. So to summarize, with Moldex3D's fiber analysis add-on, we can compare the X, Y, and Z modulus, as well as the major, mean, and minor modulus. This information is critical for understanding what effect an external load will have on your part.